Soil corrosion damage mechanisms as a part of uniform or localized loss of thickness. Description of soil corrosion based on API 571. The deterioration of metals exposed to soils is referred to as soil corrosion. Soil corrosion refers to the degradation of materials, particularly metals, as a result of electrochemical reactions occurring in soil environments. This form of corrosion is often influenced by various soil characteristics and environmental factors, making it a significant concern for infrastructure, such as pipelines, foundations, and buried structures. Here are key aspects of soil corrosion damage. Number 1 is mechanisms of soil corrosion. Electrochemical reactions. Soil acts as an electrolyte, facilitating electrochemical reactions between metallic surfaces and corrosive ions present in the soil. These reactions can result in the loss of metal mass over time. Soil moisture and oxygen levels. The presence of moisture and oxygen is critical for corrosion. Wet soil environments often promote corrosion processes, particularly under aerated conditions where oxygen is available for reaction. Soil pH. The acidity or alkalinity of the soil affects corrosion rates. Acidic soils, low pH, are typically more corrosive due to higher concentrations of hydrogen ions, while alkaline soils, high pH, may offer some protection. Microbial activity. Certain microorganisms present in the soil can accelerate corrosion through microbiologically induced processes, such as the production of corrosive metabolites, such as hydrogen sulfide from sulfate-reducing bacteria. Number 2 is types of soil corrosion. Uniform corrosion. A relatively uniform loss of material occurs across the surface of the metal, usually resulting from direct exposure to corrosive soil conditions. Pitting corrosion. Localized areas of corrosion can develop into pits, which leads to significant localized thinning and weakening of the metal. This type of damage can be particularly dangerous for structural and pressure-containing components. Galvanic corrosion occurs when dissimilar metals are in electrical contact and buried in soil, leading to accelerated corrosion of the less noble metal. Crevice corrosion. This can occur in areas where soil becomes trapped, leading to stagnant conditions that promote localized corrosion, particularly in joints, seams, or fittings. Number 3 is factors influencing soil corrosion. Soil composition. The presence of salts, such as chlorides and sulfates, can be highly corrosive. Organic materials and varying clay content also influence soil conductivity and corrosion processes. Temperature. Increasing temperatures can enhance microbial activity, accelerating corrosion rates. Electrical resistance. Soils with high resistivity, such as dry, sandy soils, may exhibit lower corrosion rates than highly conductive soils, such as wet, clay-rich soils. Number 4 is consequences of soil corrosion. Structural damage. Corrosion can lead to the failure of buried pipelines, underground tanks, and foundations, causing leaks, collapses, and environmental contamination. Economic costs. Maintenance, repair, and replacement of corroded infrastructure result in significant economic costs. Additionally, unplanned service interruptions can disrupt operations and lead to financial losses. Environmental impact. Corrosion-related leaks can result in contamination of groundwater and soil, affecting ecosystems and potentially posing health risks to nearby populations. In conclusion, soil corrosion is a complex issue that can lead to significant material degradation and structural failures. Understanding its mechanisms and influencing factors is essential for implementing effective detection and mitigation strategies, ensuring the integrity and longevity of buried structures and infrastructure over time. Soil corrosion affected materials based on API 571, carbon steel, cast iron and ductile iron. Soil corrosion can affect a variety of materials, particularly those used in underground applications and infrastructure. Here are the primary materials commonly affected by soil corrosion. Number 1 is metals. Carbon steel. This is the most commonly affected material in soil corrosion due to its widespread use in pipelines, storage tanks, and construction. Carbon steel is vulnerable to uniform and localized corrosion. Cast iron, often used for pipes in sewage and water distribution systems, cast iron can corrode due to soil conditions such as moisture, acidity, and microbial activity. Copper, generally resistant to corrosion, but can still be affected in some soil environments, particularly due to galvanic corrosion when in contact with other metals. Aluminum, while aluminum naturally forms a protective oxide layer, it can still suffer from localized corrosion in aggressive soil conditions, especially in the presence of salts and high chloride concentrations. Stainless steel, while more resistant than carbon steel, certain stainless steel alloys can still be susceptible to pitting and crevice corrosion in chloride-rich soils. Number 2 is composites and reinforced materials. Reinforced concrete, the steel reinforcement bars, rebar, within concrete are susceptible to corrosion, particularly when exposed to moisture and chlorides that can penetrate and compromise the protective alkalinity of the concrete. Fiber-reinforced polymers, FRPs generally, corrosion-resistant but can be affected by certain soil chemicals or high temperatures, leading to degradation of their mechanical properties. Number 3 is coating and liners. Protective coatings, even the most robust coatings, like epoxy or polyurethane, can suffer degradation over time, especially if moisture penetrates underlying layers or if there are defects in the application. Polymeric liners, used in various applications to protect metal surfaces from corrosion, liners can degrade over time due to chemical exposure, soil abrasion, or mechanical damage. Number 4 is soil and aggregates. Soil types, various soil types, including clay, sandy, and loamy soils, can influence corrosion rates. Soil characteristics, such as pH, salinity, moisture levels, and microbial content, play a crucial role in determining the severity of soil corrosion. Backfill materials, the type of backfill used in construction can affect the susceptibility of buried metal components to corrosion, especially if it contains high levels of salts or organic materials. Number 5 is other materials. Copper alloys, these can be affected by soil conditions leading to densification, in brass, or erosion corrosion in aggressive environments. Organic materials, organic substrates within the soil can lead to microbiologically induced corrosion, or MIC, which might not affect the materials directly but can create conditions that promote corrosion of nearby metallic surfaces. Key takeaways: soil corrosion can impact a broad range of materials, but metals, particularly carbon steel, copper, and stainless steel, are the most commonly affected. The severity and type of corrosion depend on various factors, including soil characteristics, moisture levels, and the presence of corrosive agents. Implementing proper material selection, protective measures, and regular monitoring can help mitigate the risks associated with soil corrosion. Soil corrosion critical factors based on API 571, Number A. The severity of soil corrosion is determined by many factors including operating temperature, moisture and oxygen availability, soil resistivity, soil condition and characteristics, soil type, water drainage, and homogeneity, variation in soil type, cathodic protection, stray current drainage, coating type, age, and condition. Number B. There is no single parameter that can be used to determine soil corrosivity. Instead, a number of characteristics must be combined to estimate the corrosion in particular soil as outlined in ASTM STP 741 as well as API RP 580 and API RPL 581. Number C. Soil resistivity is frequently used to estimate soil corrosivity, mainly because it is easy to measure. Soil resistivity is related to soil moisture content and dissolved electrolytes in the soil water. Number D. Soils having high moisture content, high dissolved salt concentrations, and high acidity are usually the most corrosive. Number D. Soil-to-air interface areas are often much more susceptible to corrosion than the rest of the structure because of moisture and oxygen availability. See Figure 496, corrosion of carbon steel pipe at the soil-air interface where the pipe emerges from underground. Number F. Corrosion rates increase with increasing metal temperature. Number G. Other factors that affect soil corrosion include galvanic corrosion, dissimilar soils, stray currents, differential aeration corrosion cells, and microbiologically induced corrosion. Soil corrosion damage is influenced by several critical factors that affect the electrochemical processes responsible for material degradation. Understanding these factors is essential for preventing and mitigating corrosion. Here are the key critical factors of soil corrosion. Number 1 is soil composition. Soil type, the composition of the soil, whether clay, sand, loam, or silt, determines its moisture retention, pH, and chemical reactivity, all of which contribute to corrosion rates. Salinity, high concentrations of salts, such as chlorides, sulfates, can significantly increase the corrosivity of the soil by enhancing its electrical conductivity and accelerating electrochemical reactions. Organic content, the presence of organic materials can lead to microbiologically influenced corrosion, or MIC, where bacteria produce corrosive compounds that attack metal surfaces. Number 2 is soil moisture. Water content, the presence of moisture is critical for most corrosion processes. Excess water can facilitate the movement of corrosive ions and promote electrochemical reactions. Drainage conditions, well-drained soils that retain less moisture can be less corrosive than poorly drained soils, which maintain saturated conditions that support corrosion. Number 3 is pH level. Acidity or alkalinity, soil pH affects the corrosiveness of the environment. Acidic soils, pH less than 7, tend to be more aggressive due to higher concentrations of hydrogen ions, while alkaline soils, pH greater than 7, can sometimes offer protective effects for certain materials. Number 4 is redox potential. Oxidation reduction reactions, the soil's oxidation reduction potential, EH, indicates its capacity to support electrochemical reactions. Low redox potential environments, often found in anaerobic conditions, can be particularly conducive to corrosion, especially for metals. Number 5 is electrolyte properties. Electrical conductivity, soils with high electrical conductivity permit easier ion flow, heightening the likelihood of corrosion. This is influenced by water content, salinity, and temperature. Number 6 is temperature. Thermal effects, higher temperatures can accelerate corrosion processes by increasing reaction rates and enhancing microbial activity. Seasonal variations can also affect temperature and, subsequently, corrosion rates. Number 7 is microbial activity. Microorganisms, the presence of bacteria and fungi can influence soil corrosion. Specific bacteria can produce acidic byproducts or other corrosive metabolites, facilitating corrosion processes. Number 8 is soil aeration. Oxygen availability, aerated soils can support corrosion due to the presence of oxygen, which is essential for many electrochemical reactions. Conversely, anaerobic environments may slow down corrosion processes in certain conditions. Number 9 is material properties. Material composition and microstructure, different metals and alloys exhibit varying degrees of resistance to corrosion based on their composition, microstructure, inherent protective coatings, and passive oxide layers. Surface conditions, surface roughness, cleanliness, and the presence of protective coatings affect susceptibility to corrosion. Number 10 is geological factors. Soil compaction, compacted soils can reduce moisture retention but may also trap corrosive agents against metal surfaces, potentially exacerbating localized corrosion. Soil variation, variability in soil composition and properties across a site can lead to uneven corrosion rates in infrastructure. Number 11 is external factors. Presence of dissimilar metals, galvanic corrosion can occur when different metals are in electrical contact in a corrosive environment, leading to accelerated degradation of the more anodic material. Environmental conditions, factors such as rainfall, flooding, and seasonal freezes and thaws can impact both moisture levels and soil chemistry, affecting corrosion rates. In conclusion, soil corrosion damage is a multifaceted issue influenced by a variety of factors that interact with one another. By understanding these critical factors, engineers and maintenance personnel can better design, monitor, and maintain buried structures and infrastructure to reduce the risks associated with soil corrosion. Regular assessments and mitigation strategies based on these factors are essential for the longevity and integrity of affected materials. Soil corrosion damage affected units or equipment based on API 571, Number A, underground piping and equipment as well as buried tanks and the bottoms of above-ground storage tanks, see Figure 497, coupons removed from the bottom of an unprotected steel condensate storage tank after 3 years of service. The external surface is shown. Number B, ground-supported metal structures, see Figure 498, cross-section through location, A, showing severe corrosion. The arrows point to a location that was at the original thickness. Soil corrosion can have significant impacts on various units, equipment, and infrastructure that are buried or in direct contact with the soil. Here are some of the primary units and types of equipment commonly affected by soil corrosion. Number 1 is pipelines. Oil and gas pipelines. These pipelines are particularly vulnerable to corrosion due to the harsh and varying conditions of soil in which they are buried. Water and sewage pipes, both cast iron and steel water lines can experience significant corrosion, leading to leaks and contamination. Number 2 is storage tanks. Underground storage tanks, USTs used for fuel, chemicals, or waste. USTs are prone to corrosion, especially if made from steel and in contact with corrosive soil conditions. Above-ground storage tanks, ASTs. Bases or foundations of ASTs can also be susceptible to corrosion due to moisture and soil contact. Number 3 is reinforced concrete structures. Bridges and overpasses. The rebar within reinforced concrete structures can corrode when in contact with aggressive soil, leading to structural integrity issues. Foundations and footings. The concrete may protect against corrosion, but the embedded steel rebar can still suffer from corrosion due to aggressive soil conditions or poor drainage. Number 4 is civil engineering structures. Retaining walls, wall anchors and reinforcements can be compromised by soil corrosion, affecting structural stability. Dams and levees. Embedded steel components or foundations can be susceptible to corrosion from the surrounding soil. Number 5 is electrical equipment. Buried cables. Electrical wiring or cables buried underground can corrode, especially if not adequately insulated or protected against moisture and soil chemistry. Grounding systems. Ground rods and connections can corrode, leading to ineffective grounding and increased electrical resistance. Number 6 is agricultural equipment. Irrigation systems. Pipes and fittings used in irrigation can be subject to corrosion, particularly when in contact with saline or acidic soils. Tillage and plowing equipment. Equipment used near or in direct contact with soil can experience corrosion, affecting agricultural productivity and equipment life. Number 7 is transportation infrastructure. Railway tracks and sleepers. Metal components of rail systems, including tracks and attachments, can be compromised due to soil corrosion. Foundation supports. Steel supports and pylons for roads, bridges, and tunnels can experience corrosion damage when in contact with moist soil. Number 8 is cultural and historical artifacts. Archaeological finds. Metal artifacts buried in soil can be prone to corrosion, especially if they are made from iron or other susceptible materials. Number 9 is ducts and plumbing. Ventilation ducts. Even non-metallic ducts can be indirectly affected by corrosion due to moisture and chemical interactions within the soils they are buried near. Sewer systems. Pipes and fittings in sewer systems are vulnerable to corrosion from both soil and the waste they carry. Number 10 is fuel distribution systems. Service station pumps and piping. Corrosion can affect underground piping used for distributing gasoline or other fuels, leading to leaks and environmental hazards. Number 11 is foundational elements of buildings. Building foundations. Steel reinforcements in foundations can corrode, potentially leading to structural failures over time. In conclusion, soil corrosion can impact a wide range of units and equipment, particularly those that are buried or permanently installed in the ground. Its effects can lead to costly repairs, structural failures, and safety hazards, emphasizing the importance of understanding soil characteristics and employing proper protective measures to mitigate corrosion risks. Regular monitoring and maintenance of affected infrastructure are crucial to prolonging the lifespan and ensuring the integrity of these materials and systems. Appearance or morphology of soil corrosion damage based on API 571. Number A. Soil corrosion appears as external thinning with localized losses due to pitting. The severity of corrosion depends on the local soil conditions and changes in the immediate environment along the equipment metal surface. Number B. Poor condition of a protective coating is a telltale sign of potential corrosion damage. The appearance or morphology of soil corrosion damage can vary widely depending on several factors, including the materials involved, soil composition, environmental conditions, and the specific corrosion mechanisms at play. Here are some common characteristics and forms of corrosion damage that can be observed. Number 1 is general corrosion. Uniform surface deterioration. This type of corrosion results in a uniform loss of material across the surface. The metal may appear duller or lighter than the surrounding areas. Scaling or pitting. One of the more noticeable signs is the presence of small pits, pitting corrosion, on the surface, which can lead to significant fatigue and failure over time. Number 2 is pitting corrosion. Localized holes and pits. Pitting creates small but deep holes or pits in the metal surface. These can occur in clusters or as solitary defects, often leading to structural weakness without significant material loss elsewhere. Irregular pit shapes. The pits are typically irregular, often resembling tiny craters. Their depth can be significant compared to their diameter. Number 3 is galvanic corrosion. Different corrosion rates. When different metals are in electrical contact in a corrosive environment, one metal may corrode significantly faster than the other. The affected metal surfaces may show uneven corrosion patterns, often with a more rapid deterioration at the contact points. Discoloration. Galvanic corrosion may cause discoloration and reveal a clear distinction between the two metals due to differing corrosion rates. Number 4 is crevice corrosion. Localized attack in gaps. Crevice corrosion occurs in confined spaces, such as between metal surfaces and soil or sediment, often leading to localized damage that may not be visible until significant corrosion has occurred. Staining. There may be evidence of rust staining around areas where soil or debris can trap moisture. Number 5 is microbiologically influenced corrosion, or MIC. Biofilm formation. The presence of bacteria may lead to the development of biofilms on metallic surfaces, making them appear slimy or stained. Localized pitting. Similar to pitting corrosion, biological activity can lead to localized pits, often with surrounding areas showing discolored corrosion products. Number 6 is corrosion products. Oxides and hydrated salts. Depending on the metal type and soil conditions, corrosion can result in oxides, such as iron oxide, or hydrated salts that may accumulate on surfaces, leading to flaking or scaling. Reddish-brown or greenish stains. Rust, iron oxide, can create reddish-brown stains, while copper corrosion may produce green patinas, copper carbonate. Number 7 is hydrogen-induced cracking, or HIC. Reading cracks. Cracks can develop as hydrogen diffuses into the metal, often appearing as elongated fissures or very fine cracks that can be difficult to detect unless close inspection is made. Surface blistering. Blistering may also appear if hydrogen buildup causes the metal surface to bulge or bubble. Number 8 is spalling and flaking. Fragmentation of material. The surface of corroded materials may begin to flake or spall off, creating uneven, jagged edges and exposing more susceptible areas to further corrosion. Number 9 is extruded materials. Deformation and warping. Due to corrosion fatigue, structural components may become warped or distorted, leading to visible defects in the material shape. Number 10 is signs of leakage or failure. Fluid leakages. For pipes and tanks, visible leaks or wet spots in the soil may indicate significant corrosion and impending failure of containment. In conclusion, the appearance and morphology of soil corrosion damage can manifest in various ways, often depending on the specific environmental and material conditions. Regular inspections, maintenance, and monitoring can help identify these signs early, allowing for timely remediation and repair to prevent more significant failures. Understanding these characteristics can also aid in the development of effective corrosion prevention strategies tailored to specific materials and environments. Soil corrosion damage prevention and mitigation based on API 571, soil corrosion of carbon steel can be minimized through the use of special backfill, coatings and cathodic protection. The most effective protection is a combination of a corrosion-resistant coating and a cathodic protection system. Preventing and mitigating soil corrosion damage is crucial for maintaining the integrity and lifespan of buried structures, pipelines, and other equipment. Here are several strategies that can be employed to manage soil corrosion effectively. Number 1 is material selection. Corrosion-resistant materials: use materials that inherently resist corrosion, such as stainless steel, copper, or specialized alloys, for pipelines and storage tanks. Coatings and linings: apply protective coatings, e.g., epoxy, polyurethane, or linings to metal surfaces to provide a barrier against corrosive soil conditions. Number 2 is cathodic protection. Sacrificial anodes: install sacrificial anodes made of more reactive metals, like magnesium or zinc, that corrode preferentially, protecting the primary structure. Impressed current systems: use impressed current cathodic protection systems, where an external power source is used to provide a constant current to counteract corrosion processes. Number 3 is soil management. Soil testing and analysis: regularly analyze soil for pH, moisture content, and resistivity to understand its corrosiveness and tailor protection strategies appropriately. Soil conditioning: modify soil properties, such as through the addition of bentonite or other stabilizers, to reduce corrosivity, particularly around buried pipelines. Number 4 is proper drainage. Install drainage systems: ensure proper drainage around critical infrastructure to minimize water accumulation, reducing the moisture content that leads to more aggressive corrosion. Elevate structures: when possible, elevate structures above ground level or ensure sufficient backfill to keep them out of direct contact with moisture-laden soils. Number 5 is burying techniques. Encapsulation: use protective sleeves or wrapping for underground piping and cables to minimize direct contact with corrosive soil. Proper depth: bury pipelines and structures at appropriate depths where soil temperatures and conditions are less aggressive. Number 6 is regular inspection and monitoring. Corrosion monitoring systems: implement corrosion monitoring solutions, such as corrosion coupons, remote sensing, to detect early signs of corrosion. Routine inspections: conduct regular visual checks and non-destructive testing, NDT, to identify and assess corrosion damage and make necessary repairs. Number 7 is electrochemical protection techniques. Focused ion beam techniques: advanced methods allow for localized protection or repair where corrosion has been identified. Surface modification: techniques such as anodizing or surface hardening can improve resistance to corrosion. Number 8 is environmental control. Control soil capability: control the soil environment through water management practices to minimize conditions that favor corrosion, such as reducing salinity and lowering acidity. Bio-based treatments: use bioremediation techniques to reduce corrosive substances in the soil, benefiting from naturally occurring microbes that can change environmental conditions. Number 9 is education and training. Staff training: train staff and contractors on corrosion management practices and the importance of maintaining and protecting buried systems. Best practices development: document and share best practices for construction, installation, and maintenance that include strategies for mitigating corrosion. Number 10 is design considerations. Engineering design: involve corrosion engineering during the design phase of structures to ensure that proper materials and protective measures are in place from the outset. Redundant systems: design redundant systems or protect critical components to maintain functionality even if some parts experience corrosion damage. In conclusion, effective prevention and mitigation of soil corrosion require a proactive and multifaceted approach that combines material selection, protective techniques, environmental management, and regular monitoring. Awareness and education about corrosion risks, coupled with timely maintenance and appropriate technologies, can significantly extend the lifespan of buried infrastructure and reduce the overall costs associated with corrosion damage. Soil corrosion inspection and monitoring method based on API 571, Number A. The most common method used for monitoring underground structures is measuring the structure to soil potential using dedicated reference electrodes near the structure, corrected for IR drop error. Cathodic protection should be performed and monitored in accordance with NACE RP 0169. Number B. There are many techniques for inspecting buried or on-grade metallic components. Piping may be inspected by inline inspection devices, guided ultrasonic thickness tools, indirectly by pressure testing, or visually by evaluation. The same or similar techniques may be used on other structures. Inspection and monitoring methods for detecting soil corrosion damage are essential to ensure the integrity of buried infrastructure, such as pipelines, tanks, and other metal structures. These methods can help identify early signs of corrosion and allow for timely intervention. Here are several common techniques used for inspection and monitoring of soil corrosion. Number 1 is visual inspection. Surface examination. Inspect visible parts of pipelines and above-ground structures for signs of corrosion like rust, pitting, or discoloration. Soil surface assessment. Look for signs of soil disturbance, leaks, or unusual vegetation that might indicate corrosion-related failures. Number 2 is soil testing. Soil sampling. Collect soil samples from around buried structures for analysis of pH, resistivity, moisture content, and corrosive elements, like sulfates or chlorides. Corrosivity testing. Utilize soil corrosion tests to assess the likelihood of corrosion based on chemical properties. Number 3 is corrosion coupons. Use of coupons. Install metal coupons made of the same or similar materials as the protected structure in the soil. These coupons corrode at a rate representative of the environment and can be periodically removed and measured for weight loss. Measurement techniques. Weigh the coupons before and after exposure to determine the corrosion rate. Number 4 is electrochemical techniques. Linear polarization resistance, LPR. Assess the corrosion rate through electrochemical measurements. LPR probes can be inserted into the soil to monitor the resistance of the metal. Electrical resistivity measurements. Determine soil resistivity using a 4-point probe method to assess the corrosiveness of the soil. Number 5 is cathodic protection monitoring. Potential measurements. Regularly measure the potentials of cathodic protection systems to ensure they are functioning correctly and providing effective protection. PSP, pipe-to-soil potential. Measure the electrical potential between the steel structure and the adjacent soil to evaluate cathodic protection performance. Number 6 is ultrasonic testing, or UT. Wall thickness measurement. Use ultrasonic thickness gauges to measure the wall thickness of pipes and tanks. A reduction in wall thickness can indicate internal or external corrosion. Surface scans. Ultrasonic testing can also identify flaws and defects in materials. Number 7 is magnetic particle testing, or MPT. Surface flaw detection. This method detects surface and near-surface defects. It is particularly useful for identifying cracks and pits on ferromagnetic materials. Number 8 is radiographic inspection. X-ray or gamma-ray inspection. Radiographic methods can visualize internal structures and highlight corrosion areas that might not be visible externally. Number 9 is ground-penetrating radar, or GPR. Non-destructive method. Use GPR to visualize subsurface conditions, identifying anomalies that may indicate corrosion or deterioration of buried structures. Number 10 is vibration monitoring. Structural health monitoring. SHM use vibration sensors to monitor changes in the vibrational characteristics of a structure, which may indicate the onset of corrosion and structural integrity issues. Number 11 is smart sensors and IoT technology. Remote monitoring. Implement smart sensors equipped with wireless technologies to continuously monitor corrosion rates and environmental conditions, transmitting data for real-time analysis. Data analytics. Use analytics tools to assess corrosion data to predict future corrosion trends and prevent infrastructure failure. Number 11 is aerial and drone inspections. Mapping and imaging. Employ drones equipped with cameras and sensors to assess large areas for visual signs of corrosion or surface degradation, especially in hard-to-reach locations. In conclusion, implementing a combination of these inspection and monitoring methods can provide a comprehensive approach to detecting soil corrosion damage. Regular assessments and proactive measures can help manage corrosion risks, ultimately prolonging the lifespan and safety of buried infrastructure. It is also essential to tailor the choice of methods to specific environments, materials, and types of infrastructure to achieve the best results. Thank you.